Yeah. So we basically look at the vibrations in spring mass damper systems. So the first simple case, and here the question is related to how does the differential equation will look in a spring mass damper systems with a given external force F. Okay. So yeah. So if you're actually writing a governing equation or the differential equations, first you need to simply look at the free body diagram. So let's see. Yeah. Okay. Now you have a force F acting here, external force, and this mass M is moving vertically down, so it will have some displacement x and velocity x dot and acceleration x double dot. Right? Now, if there is a spring, due to that there will be a force proportional to the displacement kx, and if there is a damper, it will have a uh, velocity proportional force cx dot. Okay. So now the total force on the system would be F minus Kx minus Cx dot is giving rise to the acceleration of mx double dot. So basically we are writing F equal to ma with all the forces. So this gives us the final equation mx double dot plus Cx dot plus Kx is equal to F when there is an external force F. Okay. Now for the simple cases when there is no external force F, Abid, can you mute? Yeah. Can you mute? So for a simple case, just a spring and mass. So there is no damper and there is no external force. So it would be mx double dot plus kx is equal to 0. In a spring mass damper without any force, it would be mx double dot plus cx dot plus kx is equal to 0. And this is for this full form, right? Yeah. So mx double dot plus cx dot plus kx is equal to f for the full case. Now for this simple spring mass systems, one of the solutions, possible solutions, you can just take cos omega nt plus b sin omega nt, and this omega n is the natural frequency given by root k by m. Okay. Now for the damper, this general solution would look like some constant omega nt into sin of, okay, here omega n is again root k by m, and omega d is omega n into root over 1 minus zeta square, and zeta would be your damping factor. One second. Damping factor zeta is equal to damping quotient c by 2 root km. Now if the damping factor is 1, such damping coefficient will be critical damping coefficient. So for zeta is equal to 1, C would be equal to critical damping coefficient, which is will be equal to 2 root k. Is that clear? Okay. Now you can, there is one more way to write this critical damping coefficient. Let's say if you want to write it in only terms of mass and natural frequency. Because natural frequency is root k by m, you can write omega n square is equal to k by m, and k is equal to m into omega n square. So if you replace k with this m into omega n square into m, so this would become 2 into omega n into m. Okay. So this is the critical damping coefficient in terms of m and omega n, natural frequency and the mass, and 2 root km if you want in spring constant and mass. Okay. Yeah, I think with respect to with just system with damper, I think these are the main things. So this is the natural frequency, this is the damping factor, and this is the critical damping coefficient. Okay. Anything else? Okay. Yeah. Now let's look at the case with the mx double dot plus cx dot plus kx is equal to f. So for this case, let's say f is some f naught cos omega f t. Okay, something of this sort. Then the general solution would look something like this: a into e power minus zeta omega n t into sine of omega dt plus theta plus some a naught cos omega ft minus pi. Okay, so if for a forced system, when there is an external force F, then this would be the general solution. And in this case, the parameters to look at are: one is the frequency ratio R, which is the ratio of the forced frequency to the natural frequency of the system. Okay. And one more thing to see here is the magnification factor. So F naught is the force which are actually giving, right? And in the spring, how much force you would be the maximum you would be getting? So because the average of this is a sine thing, and yeah, this is a transient component of the response, and this is the steady component response. Okay. So x, the spring force is kx, so a naught k. So this would be the force which you will see in the spring, and this would be the applied force. So the ratio of those two will be the magnification factor, which comes out this way. Okay. So when you have a spring, mass, force and damper, yeah, these are the important factors which you need to consider, which you need to remember. And if you have just a spring mass damper, the damping factor and the critical damping, and if it's only just spring and mass, then the natural frequency. Okay. Now with this, I think we can solve the next set of questions, which will be easier from here. Yeah. So the question is, an undamped single degree of freedom system has a response given as. So here they have given us the final response already, and we need to find the unknown coefficients a and b for given boundary conditions. Okay. So first let's look at a, or first let's see x of t is equal to a sin phi t plus b cos phi t. So this is the displacement. So how should the velocity would look? So you need to do the differentiation of the x, right? So sine derivative is cos, so phi will come, so phi a cos omega phi t minus, because cos derivative is minus sine phi. And if you are looking at x double dot, the acceleration, you again need to derive the this velocity. So phi phi is 25, a cos derivative is sine, so minus, and then minus 5 25, 5 5s are 25, b cos phi t. So if you take minus 25 outside, so it is like a sin phi t plus b cos phi t. So which is minus 25 x of t. Okay. So this is the acceleration, velocity, and the displacement. Abid, are you able to follow? Yeah. Okay, good, good. So now let's look at case A, where they have given x at time 0 and x dot at time 0. So what would be x at time 0 for the above case? Because a sine of 0 would be 0. So only b will be there, b cos phi into 0. So it will be b, just b. What will be x dot at 0? So because t is 0, cos 0 it will be 1. So 5a, sine 0 would be 0, right? So yeah. Now in a, they given x of 0 is equal to 10 and x dot of 0 is equal to 20. So this means x of 0 is b, b equal to 10, and x dot of 0 is 20, which is 5a is equal to 20. So a is equal to 4. Okay. And for case B, x of 0 is 5, x dot of 0 is 0. Okay, so this would make it x of 0 is b, so b is equal to 5, x dot of 0 is 5a. Okay, so for this the actual solution is just b cos phi t. So b is 5, so 5 cos phi t. For this case, the final solution form would be x of t is equal to a is 4 sin phi t plus b is 10 cos phi t. Okay. Yeah. So this way, if you know the functional form, and if any two conditions are given, because we have two unknowns here, a and b, you can easily estimate the values of a and b. Okay, I hope this is clear. So now let's move on to the next question. Find the natural frequency in radians per second and the critical damping coefficient for a system of, they have given the mass and stiffness. So that means K is 8000 Newton per meter and mass is 20 kgs. So can you tell how can we estimate the natural frequency now? Abhi? Yeah, we have seen the formula. So this is the natural frequency, right? Root over K by M. Yeah. So the natural frequency, because K and M are given, is just root over K by M. So square root of 8000 by mass is 20 is equal to 20 rads per second, radians per second. Okay. Now natural frequency is over. Then the second question is critical damping coefficient. So what is critical damping coefficient? Mm, uh, if you see our initial discussion, first question. So the critical damping is when the damping factor equals 1. So that is 2 root km or 2m omega n. Okay. Yeah. So if we put that 2 root km is equal to 2 into square root of 8000 into mass is 20. Okay. So is there a different formula with which we can derive this? You can also use 2 into mass into omega n. So 2 into 20 into 20, 800. Okay. So any of these two formulas you can use for the critical damping. So it's up to you based on what are the given conditions. You can use any of the two formulas. Okay. Yeah. So the main thing you need to remember is if they say critical damping coefficient, that means the damping factor is 1. Okay. Yeah. So next, let's move on to the next question. Yeah. So now they have asked us to find the damping factor for the above system if a damping coefficient of 40 kgs per second is there. Okay. So what is damping factor? C by root 2 root km, right? So from our previous discussion, damping factor zeta is C by 2 root km. And we have seen that 2 root km is the critical damping coefficient, right? So then the damping factor you can directly, because here they are asking for the above system, that means for this system, 15th question, where we already calculated the critical damping to be 800. Yeah. Okay. Hmm. Okay. So then the damping coefficient would be 40 by critical damping is 800. Excuse me. So the damping factor would be 0.05. Okay. So this is how you can estimate the damping factor if you know the damping coefficient and the critical damping, or if you know only mass and stiffness, then you can estimate the critical damping and then you can estimate the damping factor. Okay. So for all these questions, okay, next question also. So now this question is about a forced spring mass damper. So and they are asking what will be the frequency ratio at resonance. So what is resonance in this forced spring mass damper system? When will we have resonance? Hmm, anyone? Hmm? Yes. So when the natural frequency and the forced frequency are same, then you will have resonance, right? And so the what will be the frequency ratio for this case? Frequency ratio R is defined as the ratio of the forced frequency and the natural frequency. So at resonance, the frequency ratio should be 1. Okay. Yeah. And then what would be the magnification factor? So this we have seen earlier in our first question itself, where we have derived it. So this is the magnification factor formula if you know the frequency ratio and the damping factor. Okay. So let me just rewrite that. Okay. So now we know R is 1 and the damping factor is given as 0.5. So that means zeta is equal to 0.5 and R equal to 1. So what does this make this magnification factor? R is 1, so this term would be 0 plus 2 into zeta is 0.5 and R is 1. So 2 into 0.5, 1. So the magnification factor would be just 1. Okay. So now this is how you can calculate, if you know the frequency ratio and the damping factor, the magnification factor. So yeah, till this question we have actually looked at only the formulas which we derived in the first question. Okay. So these things you need to remember: the natural frequency, the damping factor, and the critical damping coefficient, and the frequency ratio and the magnification factor. If you can remember this, then it will be easier in similar questions. And the exact derivations and where this will be actually used or needed, Sar has explained beautifully in the video lectures if you follow them. Okay. Yeah. Now let's move on to the next question. So I think you may know this. So what is the equivalent spring constant when you have two springs in? This is what? Which case will this be? Parallel, right? This is two springs in parallel, and this is two springs in series. So what will you do when the springs are in parallel? What will be the equivalent spring coefficient or spring constant? Any idea? So let's look it simply like this. So let's say if this is moved below by delta x, okay, this mass, then what will be the force given by this spring? What will be the force given by spring 1 if this has moved by delta x? Any answer? So this would give k1 into delta x, right? Spring 1. Because you have moved delta x here and here, both places, you would also have k2 delta x from the other spring. Okay. So the total force, you are actually getting sum of both forces, two springs. So that's the simple way to remember. So for parallel, the spring constants, you just add them up because you are ending up with both forces. But when they are in series, if you have delta x displacement here, that delta x is divided into some components for both spring 1 and spring 2. Okay. So you can't just add the spring force. So there it actually comes out to be this way. Okay. Because here you need to add the delta x's, here you need to just add the forces in the parallel case. The spring force just becomes sum of the two springs. Here you need to do the opposite. Okay. So K equivalent here would be K1 K2 by K1 plus K2. Okay, this is when the springs are in series, one after the other, and if they are in parallel, it's just adding up. Okay, is this clear now? Yeah, that's good. Okay, now let's move on to the next question. Yeah. So the transmissibility for the case of vibration isolation will always be less than 1 if the frequency ratio is. So have you guys watched the SARS lectures? Okay, okay. So if you see those SARS lectures where we talked about the vibration isolation, so that is to have the machines isolated from the vibrations of the ground. Because let's say you have 3 4 machines in your factory or industry or in a plant, and some machine produces very large vibrations where it affects the ground also. You don't want the other machine to be affected by those, so you mount these machines on springs and systems. So that is this vibration isolation, which is are explained in detail in the class. So if that is happening, and you want this transmissibility, the force which is transferred to the machine or from the machine should be less than 1. What should be the frequency ratio? So the transmissibility directly as a formula, so ft by f0 1 plus 2 okay. So this is the transmissibility. So if you know the damping factor and the frequency ratio, then you can actually estimate the transmissibility. But here they didn't say anything about the damping, they just wanted always less than 1. So they want this transmissibility to be less than 1 always. And if the frequency ratio, so for a given frequency ratio they want it to be always less than 1. Now for the, because they said always, let's look at a case where there is no damper. That means damping coefficient is 0. So if we look at such case, then so top term this would be 0, so you will only have, so you want this force transmissibility to be less than 1, right? Then what should be the frequency ratio? So if you want square root of something to be less than 1, that should be less than 1. Because let's say if you take a 2, square root of 2 is 1.4. So 2 is greater than 1 and square root of 2 is greater than 1. But if you take 0.9, or let's take something simpler so that we can do 0.09. What is the square root of 0.09? Is 0.3, right? So this is less than 1, both are less than 1. So if you want a square root of something to be less than 1, then that should also be less than 1. Okay. So this should be less than 1. That means 1 minus r square of whole square should be greater than 1, right? So if you want 1 by a to be less than 1, a should be greater than 1. Then now you have 1 minus r square whole square should be greater than 1. So in which cases this will be possible? There will be 2 cases. So 1 minus r square less than minus 1, 1 minus r square greater than 1. So is this clear why there will be 2 cases? Because if you take 2 and minus 2, 2 square is greater than 1 and minus 2 whole square. So you you can either be less than minus 1 or greater than 1. In both cases your square will be greater than 1, right? Yeah. So if we do that, then first condition will give us 1 plus 1 2 less than r square, so r greater than square root 2, and this would give us 1 minus 1, so r square less than 0. So this is not possible, right? A square of something can't be less than 0, right? So this is the only possible solution. So r should be greater than square root 2. Okay. So when the forced frequency and the natural frequency, when you have such a case, then the transmissibility will be less than 1. Okay. Yeah. I hope this is clear. Now this you can do in multiple different ways. You can write it in. So this means forced frequency should be greater than 2 times square root of 2 times the natural frequency, or the natural frequency should be less than forced frequency by root 2. Okay. So questions can be asked in any way. You should be able to know what is correct. Okay. Yeah. So I hope this is clear. This is regarding the vibration isolation. Now let's look at one more question. Yeah. So this is a tuned mass damper system. The natural frequency of the primary and secondary systems should be. So in a tuned mass damper system, uh, you should, primary system is the system which you already have. To that you are adding some extra systems so that you can dampen out tuned mass damping. So in that case, this will be the best case when both of the frequencies, natural frequencies, are equal. So you want the natural frequency of the primary system to be same as the natural frequency of the secondary system. Okay. Uh, so you can refer to Sar's lectures where he has actually explained where you will be needing such a kind of systems. Okay. Yeah. And yeah. So in a similar case, this is a question. Yeah. We have given the primary frequency systems mass and stiffness. So mass of the primary system and the stiffness of the primary system are given. Now, what should be the tuned mass dampers frequency? Basically, they are asking what should be the frequency of the secondary system. So, can we estimate that? Mm. So, from mass and spring constant of the primary system, what can we estimate? We can estimate the natural frequency of the primary system, right? Have you been able to follow this? Both Samir and Abhi? Yeah, okay. Samir, were you also able to follow? Okay, okay. So the primary system's natural frequency is from the stiffness and mass. So by 4000 by 10. So primary system's natural frequency is 20 rads per second. Okay. So in a tuned mass damper, you should have the frequencies to be same, right? So the natural frequency of the secondary system should also be 20 radians per second. Okay. I think that is it. Yeah. I think with this, if you remember what we did in today's session now, you should be able to solve the assignment 2 also easily. Okay. Any questions? Yes, yes, yes. So this will be, I will upload this and you will be able to find the sessions YouTube also. The NPTEL team will send you a link for this, and if not, once I upload, I'll actually maybe email you in that group, or it will be uploaded. They will give you a link for Google Sheet in the NPTEL website, where you can find the YouTube lecture video and this also, and the notes also. And if they don't upload, you can actually search for in YouTube. You can search for Missionary fault diagnosis and signal processing Jan to May 2023 live sessions. This is the playlist name. No, no, no. I will upload it today in the YouTube. Yeah. This is the playlist name. You will also see in channel name. My name will be there in the channel name. NPTEL live session Sakil Reddy. So if you search that, you will most likely find these sessions. I will upload it tonight mostly. So you'll find it first thing tomorrow morning. You'll be able to see this. Okay. If you couldn't find, just email at this. I'll send you the links. Okay.